Cool. How's everyone doing? Awesome. So welcome back to another exciting session of CE 397 Control Theory for Smart Infrastructure. Let's just recap quickly what we talked about last time. So last time we looked at using Laplace transforms to solve different types of LTI systems. We looked at systems with distinct roots, which we solved through the technique of partial fraction expansion. We looked at systems with repeated roots, and we showed a method for using partial fractional expansion along with differentiation to determine the response for systems with repeated roots. And we also looked at the case of systems with conjugate pair poles, and we looked at an example of a structural system and how we could use a technique called completing the square to compute the response for a higher order system using the frequency domain. Okay, and we worked partially through that structural example. Just in the interest of time, I'm not going to finish that example, but in the course packet, there is a full example worked out for you to look at, which will be helpful for a problem on homework 3. So there is a structural problem on homework 3 that is similar. So take a look at that example in the course packet as you are working through homework 3. Okay. So today we're going to be taking a step back and having a bit more of a conceptual discussion. So previously we talked about how the frequency domain, how Laplace transforms are useful for solving the particular solutions to LTI systems, but they also provide us with a lot of other useful information about the system. In particular, for the purposes of today's lecture, the system in the frequency domain gives us a lot of useful information about the stability of the system, which will be especially useful for control, which we will be getting into starting next week. So today's lecture, we're going to be looking at poles in the complex plane and their role in determining the stability of an LTI system. We're going to look at both continuous time and discrete time cases. And then towards the end of class, we'll be looking at block diagrams, so block diagram algebra, and we'll be looking at a few examples of feedback that will be very illustrative for our use of controls next week. Okay, are there any questions on the material we've covered so far or where we're going before I move on? Did you have a question, Jimmy?
Sorry, so when you, on the last slide, when you talked about conjugate pairs, I don't remember explicitly saying that the poles have conjugate pairs.
Right. So when I say conjugate pair poles, it's if you have a set of poles that are complex, that are conjugates of each other. So those poles that are complex will always come in pairs. And it just comes from, finding the root of a polynomial that is complex. Generally, they will always come in complex conjugates. Right. Yes. So complex poles will always come in conjugate pairs. You'll never get, just one complex pole just by itself. They'll always come in pairs. Okay, good question. Are there any other questions about the material we've covered so far? Okay, great. So let's go ahead and get started. First, let's take a look at poles in the complex plane. Today, we're going to find out where the name poles comes from. Okay, so it's important to remember that when we're talking about poles or transfer functions of the frequency domain, that we're working in the complex plane rather than the real number line. So let's take a look at the transfer function just of a generic system and what it looks like in the complex plane. So our system transfer function HS, you could think of it as a function with its domain over the entire complex plane. So if you visualize it in the 2D plane, like so. You have the real axis, so this is the real part of S, and you have the imaginary axis, which is the y-axis here. So the system transfer function, it holds important information about the system, which we are going to go over. But I wanted to make it a point that the system transfer function is a function over this 2D plane. So you can think of it as essentially coming out of the page. Right. So we might have some contours here, for instance, representing the transfer function coming out of the page. Okay, so it's a function over this entire 2D plane that's coming out of the page. So these contours may just represent the function coming out of the page towards us. Okay, so we have that our transfer function is some function in a 2D plane, in the complex plane. So what do the poles and the zeros of the transfer function look like in this plane? Let's ask, what do the poles and zeros look like? So we have that our transfer function h of s, as before, we can factor it into a set of zeros and poles with the zeros on the numerator. So we have s minus zi. This is for I equals 1 through n. Actually, this should be m, as in Mike, for the numerator. On the denominator, we have the product from I equals 1 through n, as in November, of s minus pi. So on the numerator, we have the product of the zeros, which I'm going to denote as O. And on the denominator, we have the product of the poles, which I'm going to denote as X. Okay, so let's just take an example transfer function. We're looking at it in the complex plane. I'm going to draw the complex plane here in 2D. And let's just say that we have a couple of different zeros and poles. Here's the real component of S. This is the imaginary component of S, our complex variable. And let's say we just have two zeros on the real axis. So we have a 0 here and a 0 here. And let's say we have three different poles, one on the positive part of the real axis, and then two conjugate pair poles on the negative side of the real axis. So what does this look like in terms of the actual transfer function? Let's draw it out in 3D. And I'm not the best at drawing in 3D here, but we're just going to make it work. Okay, so this here is our real axis. We have the imaginary axis kind of coming out like this. So this is the imaginary component of S. And then vertically, we have what I will just call the magnitude or absolute value of our transfer function. So as before, we have two zeros on the real axis, one right here and one right here. And we have three poles, one on the positive side of the real axis, and then two conjugate pair poles on the negative side of the real axis. So what does this look like in the complex plane? So first of all, what is the value of h of s at one of these poles? Infinity, right? Why is it infinity? Yeah, so if we plug in if we plug in pi to the denominator here, we'll find that this expression for h of s goes to infinity. So what you'll get at the poles is around the poles, you will have, let me try to draw this a little bit better. You will have our function increasing until it goes up to infinity at the location of the pole itself. So you get these kind of tent pole looking things. This is where the name poles comes from. So for each of these poles at the pole, the value of our transfer function approaches infinity. Okay, so very good. So let's just draw those out. Okay, and similarly for this pole here, we will also get that the value of the transfer function goes to infinity here. Okay, what about at the zeros? What is the value of our transfer function at the zeros? Okay, 0, right? Yeah. So if we are thinking about this transfer function as kind of this terrain, as this terrain map at the poles, that's where the terrain creates mountains up to infinity, and the zeros are the location where the terrain goes down to 0. So you might have, for instance, the terrain moving up in between these two zeros, but at 0, it's pegged exactly to 0. I note here that I'm talking about the absolute value of our transfer function, just to make it easier to draw. But you may have poles that go to negative infinity as well, or parts of this transfer function that are negative as well as positive. Okay. So all this is to say that when you're visualizing or thinking about the transfer function, it is a function over the entire complex plane. So it's a 2D function. You can think about it as a function that is coming out of that plane that makes kind of a terrain. And at the poles, that terrain goes up to infinity. At the zeros, it goes to 0. Okay, are there any questions about the transfer function conceptually before we move on? Okay, great. Okay, so remember that our transfer function h of s is equal to the impulse response in the frequency domain. Okay, so remember this identity. The transfer function is equal to the impulse response of our system in the frequency domain, or if we're expressing in terms of its partial fractional expansion, we have that h of s is equal to the scaled sum of the poles in the denominator. So we can write it as C1 over S minus P1 plus C2 over S minus P2, and so on, all the way to Cn over S minus Pn, assuming we have n different poles. Okay, so this implies something important. So what happens if we take the Laplace transform, the inverse Laplace transform of this entire expression? We get that each one of these terms produces a term in the impulse response, right? Because the transfer function is equal to the impulse response in the frequency domain. So, you know, assuming P1 is just a single pole here, what is this term if we take the inverse Laplace transform? Yeah, so this will be C1 times e to the P1t. Right? And similarly, this will become C2 e to the P2t. And so on, all the way to Cn e to the Pnt. So essentially, the transfer function tells us almost everything we need to know about the response of the system, because each one of these poles produces its own term in the impulse response. The impulse response simply being a linear combination of these different terms. In particular, for the purposes of today's lecture, the transfer function tells us essentially everything we need to know about the stability of the system. Now, I haven't defined stability for you yet. There are different definitions of stability that we'll get into later in this class, but does anyone have an idea of what I mean generally by stability? Does anyone just want to put in their own words, what would make a system stable or unstable? If it trends towards a steady state, so that is true. Yes, so a system is stable if it trends toward a steady state. So, right, so there are some caveats. So trends towards a steady state. Usually when we talk about trending towards a steady state, we want it specifically to trend towards 0, which would make it asymptotically stable. So I'll give you a definition of stability for now. So this will be our definition of stability for the purposes of today's lecture, and we'll get into more formal definitions later. So I'm going to write definition of stability for now. Okay. And I will express it as follows. A system is stable if the response remains bounded given a bounded input. So this is a particular definition of stability that I'm just going to use conceptually for now. This is actually called BIBO stability, or bounded input, bounded output stability, which we'll talk about a little bit later. But just for the purposes of thinking about stability right now, think about the system as being stable if it remains bounded given a bounded input, meaning that the input is not infinite. Okay, or equivalently, the homogeneous response remains bounded as t goes to infinity. Okay, so looking back at our transfer function in the previous slide that we have expanded, we can see that for each of these terms, under what conditions would these terms lead to instability? Under what conditions in terms of the poles of the system would the response become unbounded as time goes to infinity? Right, if pi has a real part that is positive, right? Right, so that's what I mean by stability. And in this case, the poles tell us if the system is stable, because if any of these poles have a real part greater than 0, the response to the system, no matter what the input is, will go to infinity. Okay, so that's kind of generally what I mean by stability for the purposes of class today. We're going to go through different examples of poles, look at the response, and characterize whether the system is stable or not. So let's go through poles, their locations in the complex plane, and whether or not that leads to a stable output. Okay, so we have a complex plane here. And what I'm going to do is I'm going to go around, I'm going to look at different poles, different locations of the poles in this plane, and I'm going to ask for your help in determining what the response looks like and whether the system is stable or unstable. So we have the real component over here on the x-axis, the imaginary component over here on the y-axis. Let's look at poles in a couple of different locations. I want you to help me figure out what the response looks like for a pole in that location. So what does the impulse response look like for a pole in a given location? And does that pole lead to a stable or unstable system? Okay, so let's go through. First, let's just look at a single pole over here on the real axis, on the negative side of the real axis. So what is the impulse response corresponding to that pole on the negative real axis? Right. So let me just kind of help you out here. So if we have a pole on the negative real axis, the transfer function corresponding to that pole will be of the form something like, let's just write it as C1 over, or Ci over S plus Pi. Right. Okay, what does that become if we apply the inverse Laplace transform? Yeah, so this will become Ci e to the negative Pit, right? Okay, so we can confirm that if we go back to our table of Laplace transforms. If we have a function of the form 1 over S plus A, it becomes e to the negative At. Okay, so let's write that out. What does this look like? We have that the response corresponding to that pole looks something like this, right? So it is exponential decay. Okay, very good. Okay, what if we have a pole on the real axis, but located more over to the left here? What does the response look like for that pole? Just visually. So first of all, what's the general type of response going to be? It's going to be the same. What will be different about it? Right. So it'll decay faster, right? So we will get a steeper decay. Let me just make it a bit more dramatic here. Okay, there we go. Okay, so it's going to decay faster. Okay, very good. Okay, let's keep things going here. What if we have a pole on the real axis, but on the positive side of the real axis? Right, so you'll get exponential growth. Okay, very good. So it will look something like that. All right, and if we have a pole further over here, you will get exponential growth, except it will grow faster. Great. Okay, so just to test, is this system stable or unstable? Stable. So this pole is stable, right? I shouldn't say system. This pole is stable. This pole is stable. What about these two? These are bad. These are unstable. We don't want these. Okay. Later on, we'll be showing how we can use control to eliminate unstable behavior, or how we can develop control strategies that are not unstable. So it is generally something we want to avoid. Okay. All right. Let's take a look at another set of poles. Let's say we have a pair of conjugate poles on the imaginary axis. And again, these come in conjugate pairs, so these are always together. Okay, so what will the response look like for a pair of conjugate poles on the imaginary axis? It will be a sine or a cosine, exactly. So actually, let me make it clear that this is centered at 0 here. So this will be a sine or a cosine. Okay, here's an interesting question. Is this stable or unstable? Is this stable or unstable? Is it stable? So this is actually what we would call marginally stable. It turns out that for this pole here, we can find an input that will cause this, cause the response to become unbounded. So this is what's called marginally stable. So let me just write out what each of these are. So this is stable, stable, unstable, unstable. This is marginally stable. Okay, and we'll talk a little bit more about what that means. There'll be a problem on the homework specifically where you will find a input that will drive the response of this marginally stable system to infinity as time goes to infinity. And as a hint, it has to do with a concept called resonance. Okay, so think about that when you look at the homework. Okay, so in general, we want to avoid marginal stability. We want to drive the system to be asymptotically stable such that it decays to 0. Okay, very good. Okay, so what if we have a pair of conjugate poles on the negative side of the real axis? What will this response look like? What will this response look like? Any guesses? So it'll be a damped oscillation, right? So it will be a oscillation that asymptotically approaches 0. So it'll be a oscillation with exponential decay. So we can draw the envelope. This is exponential decay. Okay, so is this stable or unstable? Or marginally stable? Which one is this? This one is stable, right? This decays to 0 as time goes to infinity. All right, very good. Now, what if we have a pair of conjugate poles on the positive side of the real axis? What will that response look like? And don't all shout at once here. What does it look like when we have a pair of conjugate poles? What does the impulse response look like? What does the impulse response look like for this pair of poles? Yes, so it'll be an exponentially growing sine or cosine. Okay, and we can draw the envelope here. And is this stable or unstable? Unstable, very good. All right. So just looking at all of these different cases here, what can you infer about the stability or instability of the system based on the poles? What conditions on the poles will determine if the system is stable or unstable? Oh, actually, before I do that, one more case here. What if we have a pole at the origin? What will the response look like if we have a pole at the origin? Yeah, so it'll just be 1, right? How do we know that? Yeah. So just to be clear, this is corresponding to this. Let's look at what does so if we have a pole at the origin, we have that our transfer function is equal to Ci over S. Okay, if we take the inverse Laplace transform of that, we get what? Ci times the step function, right? Okay. So it is a constant value. Is this stable, unstable or marginally stable? Stable, unstable, or marginally stable? Stable? Is it stable or marginally stable? You think it's marginally stable. Why do you think it's marginally stable?
I can't think of any input
Well, what if, so we have, for instance, that y of s is equal to h of s times u of s, right? Let's just call this y I of s, h I of s, u I of s. Okay, what if our h I of s is ci over s, and our input is the step function? This becomes ci over s squared, right? What does this become in the time domain? Yes. So this becomes ci times t. Does that remain bounded as time goes to infinity? No. So this will continue to grow forever. So this is marginally stable. Note that you'll be doing something analogous on the homework, but for the case of a sinusoid instead of a step function, you'll be finding that input that drives it to infinity. And it will look somewhat similar. Okay, so what are some, just based on the figure we've drawn here, what conditions on the poles determine stability versus instability? Right. So that is exactly right. So let's define the stability in terms of the poles. Okay, for continuous time. I'll just write this as CT. Okay. So let me write it like this. If the real part of a pole PI is greater than 0, the system is unstable. If the real part of the pole is less than 0, system is stable. So one question, does this condition need to hold? So first of all, let's look at the stable case. If we have some poles that are with real part less than 0 and some poles with real part greater than 0, is that system stable or unstable? Let's go back to our expression here. So let's say we have some poles that have real part less than 0, some poles that have real part greater than 0. Is that system stable or unstable? Unstable. Why is that? Right. So the total response will be the sum of all of these different terms corresponding to the poles. So if any one of them is unstable, then the entire response will be unstable. Right. So in order for it to be stable, all of the poles have to be stable. If any of those poles are unstable, the entire response is unstable. Okay, so let's go and rewrite that in our condition expression here. So if the real part of the pole is greater than 0 for any pole PI, the system is unstable. If the real part of the pole is less than 0 for all poles PI, then the system is stable. Okay. If the real part of the pole is equal to 0, then we can say the system is marginally stable, or that the response corresponding to that pole is marginally stable. So I'll just write response corresponding to pi is marginally stable. However, it's also possible for the system to be unstable if the poles are at the zero part of the real axis, even without the special input that drives it to infinity. So let's take a look. Let's take a look back at our figure here. There's a couple cases here that we've neglected. Okay. What if we have repeated roots? What if we have repeated roots? Let's say repeated roots right here. Okay, what will the response look like if we have repeated roots on the real axis, on the negative part of the real axis? Yeah, so if we have repeated roots, let's say that our hi of s is something like ci1 over s plus pi plus ci2 over s plus pi squared. Okay, this term here will become something like t times e to the negative pi t, right? Okay, so what will the response look like? I think Jimmy basically gave the answer here. You'll get something that looks like this. You'll have the exponential part, but it's being scaled by that time term. Okay, so at time 0, it'll be 0. It rises up and then gradually goes back down. Is this stable or unstable? This is stable, right? Why is it stable if it has that time term in there? Yeah, so the exponential term will decay faster than the time term grows. So it decays faster than the linear time term grows. So this is stable. All right. What if we have repeated roots at the origin? And let me erase this color here and write this in blue. What if we have repeated roots at the origin? What will that look like? What will the response look like if we have repeated roots at the origin? Yeah, so it'll be equal to t, right? So the response corresponding to that pole will be linear and increasing. Okay, and we know that this has to be unstable. What if we have repeated roots that are conjugate pairs? So what if we have repeated roots where these conjugate pair poles are? What will the response look like there? Just reasoning by analogy here. So in the case of repeated roots at the origin, this constant turned into a linear line, right? What would this sinusoid turn into? Yeah, linearly increasing. So let's draw it out. So this becomes a linearly increasing sinusoid with time. And is this stable or unstable? This is unstable. Okay, so when you have repeated roots, you have to be careful because if you have repeated roots and the real component of your root is equal to 0, you can have an unstable system even when your real component of the root is not greater than 0. Okay, so just be aware that repeated roots can cause problems for stability. This is something you'll sometimes run into when you're dealing with integral control, which we'll be talking about next week. You can actually create instability in the system by creating repeated roots. Okay, great. Are there any questions just on our journey through the complex plane here? Any questions on stability, poles in the complex plane, their responses? Anything else? Cool. All right. So we can summarize as follows. If the real component of the pole for any pole is greater than 0, the system is unstable. If the real component of the pole is less than 0 for all poles, the system is stable. If the real component of the pole is equal to 0, then you can consider that system to be marginally stable, in that it could become unstable depending on the input or depending if there are repeated roots. Okay. All right, so let's just summarize here and also talk about the difference between continuous time and discrete time systems. So let's talk about stability regions. Let's first look at the continuous time case. And we have our complex plane here. All right. This here is the imaginary component of S. This is the real component of S. And we have that the response corresponding to some pole is equal to e to the p1 or e to the pit times some constant. I'll just say ci. So I want to shade the region of this plane that is stable. Can you tell me where I need to shade in? Sorry if it's going a little bit slow here, but I just want to make this next point clear. So if I were to shade in a region on this plane, where would I shade in the region that is stable? The left-hand plane, right? So in controls, you'll often hear the term open left-hand plane. The region of the system that is stable, or the region of the transfer function that is stable here, is the left-hand plane. So the left-hand plane, this is the region that is stable for a continuous time system. The right-hand plane is unstable. And of course, if you are on the imaginary axis, then you may or may not be stable. So this part here is marginally stable. Okay, let's take a look at discrete time systems. So just like with the continuous time case, our poles in the discrete time case are also on the complex plane. Here, instead of S, we'll be using a variable Z, but it means essentially the same thing. Just to note, I don't cover it in this class, but for discrete time systems, there is an analogous transform to the Laplace transform called the Z transform, which does essentially the same thing that the Laplace transform does in continuous time. So in the discrete time system, we have the imaginary component of Z, the real component of Z. And our system response, we can write that the response for xi at time index k is equal to pi to the k times some constant, which I'll just write ci. Okay, so in the continuous time case, remember that if we're finding the homogeneous response, for instance, it's of the form e to the pit. For the discrete time case, instead of the exponential function, we exponentiate the pole. So for the discrete time case, what region of this plane is stable? First of all, what values of pi will tend towards infinity as time k goes to infinity? Greater than 1. So we can draw here on the real axis 1 and -1. We know that if the pole is outside of that region, the system's response is unstable. What about if pi has an imaginary component? What if, for instance, pi is 2 times the imaginary unit? Would that be stable or unstable? Yeah, so it will oscillate between negative and positive, right? But it will still go to infinity if the pole has an imaginary component greater than 1. So we can define the region of stability as being the circle in the complex plane. So here we have j, here we have -j, and our region of stability is actually just the unit circle in the complex plane. Yikes. I am really not great at drawing circles here, but here we go. All right, and we're going to shade this in. So for discrete time systems, the region of stability is the unit circle. Everything outside, everything the light touches is unstable. Okay, so I just want to note that for the case of discrete time systems, these notions of stability and instability are the exact same as the type of instability that you encounter in numerical modeling. So for instance, if you do work in hydraulics or fluid mechanics, you'll often have to define your discretization such that the system is stable. That notion of stability is the exact same as this notion here. In particular, when you're doing CFD solvers, computational fluid dynamics solvers, hydraulic solvers, some of you work in contaminant transport, you need to ensure that the poles of your system, or eigenvalues, if you have a system of equations, you have to ensure that those poles lie inside the unit circle. So that notion of stability is the exact same kind that I'm talking about here. So if you have ever worked with the CFL conditions, those are equivalent to the conditions I'm showing here. All right, are there any questions on these regions of stability before I move on? Any questions? Cool. All right. So I'm going to very briefly talk about zeros. So it turns out zeros are not really as important as poles in terms of affecting the system response, but they do have some effects. So zeros, remember that we can write our transfer function as the product of the zeros on the numerator over the product of the poles in the denominator. So this is m, this is n, I. Okay. And as before, you can write it as C1 over S minus P1, yada, 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 to Cn over S minus Pn. So zeros, effectively, what they do is they modify the gain associated with each pole so that they modify these scaling factors C1 through Cn. So just to summarize, zeros modify the gain associated with each pole. So let's go through a couple examples. I'm just going to give two quick examples, and then we're going to move on to feedback in a second. Okay, so let's look at a transfer function h1 of s. It's equal to 3 over s plus 1 times s plus 4. Okay, if we do partial fractional expansion, first of all, how many zeros are there in this system? 0. There's no zeros here. Trick question. There's 2 poles. So yes, two poles and no zeros. Okay, so this system does not have a 0. If there were a 0, there would be an s somewhere in this numerator. Okay, so tricky question. Okay, so it turns out if you do PFE, partial fractional expansion, you get something in the form 1 over s plus 1 minus 1 over s plus 4. Okay, if you take the inverse Laplace transform, what does that become? So what does this term become? Take the inverse Laplace transform. Yeah, so you'll get e to the minus t. Very good. And then this will become, yeah, e to the minus 4t. Very good. Okay. Now let's say we, instead of having this system here, we have a system of the form h2 of s, where the denominator is the same. So we have s plus 1, s plus 4. Now in the numerator, we'll have a 0. Okay. And what is the 0 of this transfer function? -2. Yes, very good. Okay, so it turns out if you do partial fractional expansion, I'm not going to do it here. If you do PFE on this transfer function, you will get a separated transfer function of the form 1 over s plus 1 plus 2 over s plus 4. Your corresponding impulse response will be e to the negative t plus 2e to the negative 4t. Okay, so the general form of the impulse response is the same. Okay, those terms are still the same. It's just that the 0 changed the scaling applied to this second term here. So zeros in general, they're not as fundamental to the system response as the poles are, but they do modify the gain associated with each pole relatively. And in particular, just kind of as a rule of thumb, if you have a 0 located near a pole in the complex plane, that tends to attenuate or lessen the effect of that pole. But in general, it's hard to characterize a priori what the effect of the zeros are going to be. You kind of just have to inspect it. Okay, are there any questions on zeros before I move on? Okay, so the next thing we're going to do is pretty fun. Just are there any remaining questions on zeros, poles, stability, or anything else we talked about today? No? Okay, great. I guess I explained it pretty well then. So the next thing we are going to look at is block diagrams. So I'm going to be skipping some material from the class notes, but this is an important concept. This is going to be especially important when we get into control next week. You'll find that control engineers will often think about problems in terms of these block diagrams, where you have different blocks representing different functions feeding into each other or feeding back on themselves. Have any of you ever used Simulink in MATLAB? Have you used Simulink? Anyone else has used Simulink? So Simulink is a product produced by the folks that made MATLAB. And it's entirely built around these block diagrams. It allows you to represent systems using block diagrams to make it a bit easier to think about and design control strategies. So this is an important practical skill. It provides a nice way to think about systems with multiple interacting components. Okay, so I will just write provides a way to conceptualize systems with multiple interacting components. And it turns out we've actually been using block diagrams all along, but in a very simplified way. I presented them in the very first class. Let's say we have a system represented by its transfer function. We have some input, U of S. Okay, and applying that input to the transfer function yields Y of S. Okay, so if we're working in the frequency domain, we know that the response Y of S is equal to what? Yes, so it's equal to H of S times U of S. Okay, so if we're working in the frequency domain, these block diagrams work exactly the way we would think about them, right? We can take an input. If we apply it to a block, we simply get that block multiplied by our input, and that produces some output, in this case, Y of S, okay? So again, if we're working in the frequency domain, it works intuitively in the way that we think it would work. Okay, so let's look at a couple of different topologies for block diagrams. Let's look at blocks in series. All right, so let's say we have an input U of S. It's going into a transfer function H1 of S. From that transfer function, we get an output, which we will call X of S. That goes into another transfer function that we'll call H2 of S. And the output of that transfer function applied to the input is Y of S. Okay, so we know from our previous slide that XS is equal to U of S times H1 of S. Okay. We know that Y of S is equal to what times what? X of S times H2 of S. Okay, so we can expand this out. We have that Y of S is equal to U of S times H1 of S times H2 of S. So if we have a system where we have blocks in series, we can combine these two blocks together. Okay, what if we were to rewrite this system? We can rewrite this as our input U of S going into a single block, which I'll call H bar of S, which produces an output Y of S. Okay, where H bar of S is equal to H1 of S times H2 of S. So if you have two blocks in series, you can obtain an equivalent block by multiplying those two functions together. So note that each one of these here is a function. H1 of S is a function, H2 of S is a function in the frequency domain. The net effect of two blocks in series is to multiply those two functions together. All right, any questions? All right, awesome. So I'm gonna pick up the pace here a little bit. Let's say we have blocks in parallel. Okay, so we have a function U of S. We're going to split it into two parallel paths here. Okay, so this is U of S here. On the upper path, it's going to enter H1 of S. On the lower path, it's going to enter H2 of S. These are both transfer functions here. And then these are the outputs of these two blocks are going to reconverge and be summed at a junction. And this will produce our net output y of s. Okay, so you can reason about this kind of intuitively. We have that y of s is equal to, if we just follow these paths, we have that y of s is equal to u of s times h1 of s plus u of s times h2 of s. Okay, and we can group those together so that we have us times quantity h1 of s plus h2 of s. So the net effect is, if we have two blocks in parallel, we can define an equivalent block h bar of s such that u of s entering h bar of s produces y of s, and h bar of s is equal to the sum of h1 of s and h2 of s. So these block diagrams work in an intuitive way. If you have blocks in series, that's equivalent to multiplying those two blocks together. If you have blocks in parallel, that's equivalent to adding the two blocks together. Are there any questions on this concept before I move on? All right, so let's go through an example. We're going to use blocks to, did I go too fast there? Or no? Okay. We're going to use blocks to represent a structural system. So often blocks are, block diagrams are useful for representing systems with multiple different components. So we can use it in this case to represent a structure with an accelerometer. I don't know how to spell this right now, but I'm just going to go with this. So often a block diagram is useful if we want to represent not just the state of the system itself, but our observed output of the state. Okay, so in this case, we have our structure as before. It has stiffness K, damping C, mass M. We're going to have some input, which I'll call U of T in this case. And we have a displacement, which I will call X of T. But this time, we're going to have a sensor located on the structure that's going to measure the acceleration. So sometimes you'll have inertial measurement units, for instance, that can measure the acceleration of a structure or just any object that you're trying to measure. It's often easier to measure acceleration than to measure displacement directly. So we know that the transfer function of the structure itself is equal to 1 over ms squared plus cs plus k, right? Okay, so let's say we want to represent the output of the sensor. Let's say we want to represent what the output of the sensor is. So we can represent this using a block diagram. We have the input of the system goes into a transfer function hs of s that represents the dynamics of the structure, and that produces some displacement x of s. Okay, and if we want to represent the output of the sensor, we can feed that displacement into a second transfer function, which I'll call HA of S, representing the accelerometer. And that accelerometer outputs what I'll call A of S, which is the acceleration. So what would be a good choice for the transfer function of the accelerometer? What would be a good choice for the transfer function of the accelerometer? Okay, so we want to go from displacement. We want to go from displacement to the acceleration, right? What is this in the frequency domain? x of s. And what is this? What is x double dot of t in the frequency domain? Yeah, so it'll be s squared times x of s. So what's a good choice for the transfer function that represents the accelerometer? Close. So we want something that transforms x of s into the acceleration. That would be, it would be s squared, right? What would 1 over s squared be? So 1 over s squared would represent integrating it twice, right? So if you multiply something by s in the frequency domain, that differentiates it in the time domain. If you multiply by 1 over s, that integrates it in the time domain. So we have that our overall transfer function representing the output of the sensor, the measured output of the sensor is equal to hs of s times ha of s, which is equal to s squared over ms squared plus cs plus k. All right. I think I'm going to save the rest of the material for tomorrow because it's really what I'm about to show next is very important. And I don't want it to be the last thing you see right before the bell rings. So I'm just going to save the next part for Tuesday. And next week we will get into control, the namesake of this class. This is something you definitely haven't seen before, I don't think. And I think it's going to be really exciting. So stay tuned. And we have a couple minutes left. So actually, I would like to talk to some of you individually, if just after class, if you want to come schedule a time to talk about your projects, okay? All right. And with that, I will end the meeting. Thank you.